In this video, we will look at calculating the dissociation energy of the excited state, and also how we can find out information on vibrational constants for the excited state. We have previously looked at determining dissociation energy of the ground state using a Birge-Sponer extrapolation to sum up the individual vibrational transitions in the ground state to the point of dissociation. Now that we are considering the excited state, we will label this ground state dissociation energy with a double prime, D0 prime prime. We can take this approach in the excited state. If we know some of the vibrational energy differences in the excited state, we can again extrapolate to the point of dissociation using Birge-Sponer and calculate the excited state dissociation energy D0 prime. The single prime denotes that we are looking at the excited state. As before, we can see that there are two ways of describing dissociation energy. D0 prime is the energy difference from the 0 point energy to the point of dissociation, and dE prime is the energy difference between the bottom of the well to dissociation. Therefore, these values just differ by the 0 point energy. The Birge-Sponer extrapolation is based on this equation, where we are expressing the energy differences between vibrational states, which is related to the oscillation frequency and the anharmonicity constant. Because we are dealing with the excited state, we annotate these with a single prime. It is typical to express omega bar E times Xe as a product, so there is just one prime. We are dealing with excited vibrational states, which we describe as V prime. The area under the curve is the dissociation energy D0 prime as before. Here is the data we are given. All of the transitions are from the V prime prime equals 0 state, in other words, the ground vibrational state in the ground electronic state. Transitions are to a series of vibrational states in the electronic excited state, labelled V prime. We can see then that the difference between two successive transitions is equal to the difference between two vibrational states in the excited state, the amount we are looking for. Birge-Sponer will allow us to sum up all of these differences we know and extrapolate to dissociation. Therefore, we can calculate the differences in energy by the values we have, not many in this case, and prepare our plot of delta E versus B prime plus 1. Here is our plot. We wish to calculate the area under the triangle, but we do not have the graph beginning at the origin. Therefore, we need to find the equation of the line from the slope and the point on the line, and hence find the value of y when x is equal to 0 and of x when y is equal to 0. Then we can calculate the area of the triangle. From this plot, these points are 167.57 and 51.56, so the area, which is equal to D0 prime, the dissociation energy, is equal to 8640 wave numbers. Because our plot matches that of the equation shown, we can see that the intercept is equal to the vibrational frequency in the excited state, so we can easily calculate this value, as well as the product omega bar E Xe prime from the slope. Finally, we are asked to calculate the dissociation energy dE prime. This differs from D0 prime just by the 0 point energy. On the vibrational spectroscopy lectures, this is given by the equation shown, although because we are approximating with Birge-Sponer, it is fair to approximate the 0 point energy as being half the vibrational frequency. Summing our values, we can calculate dE prime.